This is EE698G, lecture 18. So the project 1 statement has been uploaded. You'll be designing a DLL using Cadence Virtuoso. So the same VirtualBox setup that you are using for EE613 course, you can utilize the same thing. So if you have already installed that, you don't have to do anything additional to get the tool access. For those of you who have not installed it, I have uploaded the instructions on how to install it. Okay, so we'll arrange one TA session next week so that in case you have any doubts with the tool setup, you can clear it before the midsem break starts. Right. The day after the midsem break ends.
No, 25.
25. Oh, so then it will be the day after the midsem break ends. I'll change the deadline. So the deadline will be on Monday or Tuesday after you come back from the midsem break. Right, so that you will have that complete break to design the DLL. Is that when the break ends? Yeah, 30th. Right, 1st April. Right. Okay, so any other questions? So then, so we have now seen the relationship between the phase noise power spectral density and the voltage power spectral density, right? And to get used to these notations a little bit, we were solving certain problems. So in particular, you were looking at a VCO. What is a VCO? Voltage controlled oscillator. So if I give a VC at the input, what is the frequency at the output? You can refer to your notes and then tell me the answer. Some free running frequency omega naught plus KVCO into VC, right? Sorry? It was covered in the previous lecture. So basically the characteristic will look like this. On the y-axis you have omega out, on the x-axis you have VC, and you have some characteristic that follows this shape. So when VC is 0, it is at omega naught. Yeah. What's the difference between VCO and a VCDL? What's the difference between a VCO and a VCDL? Okay. So in a VCDL, this is a voltage controlled delay line, right? If you give an input, that input comes at the output after a delay TD. And this TD is the function of VC, where VC is what you use for controlling the VCDL, right? Now, a VCO, like I said, a quick way to think about a VCO is where you take some number of tunable delay elements. Right? Let's say I took 3 tunable delay elements. If I connect it in open circuit as it is, I call this as in, if I call this as out, and this is my VC voltage, then this is a VCDL. Now imagine that I shorted its input and output. So using a VCDL, we are constructing a VCO. Using a VCDL, you can construct a VCO. VCO can be constructed using several other methods. This is one of the methods. Now, if I make a ring, this is basically a ring oscillator, right? If I make a ring oscillator like this, what is the frequency of oscillation here? 1 upon 2n? 2n into delay of each element, right? What is 2n here? Right. Now, given that I have used 3 inverters, what should I replace this with? 6. Right. So now as you change your VC, you know that the TD is going to change. And if TD changes, the oscillation frequency will also change.
So in VCDL, we change, like the TD is changed, so that doesn't affect the frequency. But in this, since we are shorting the input and output, the frequency is also changed because of changing the TD.
Correct. Also, in a VCO, the only input you need to feed in is VC. Right? In a VCDL, you had to feed in some voltage domain input, and then you were observing the output, and the delay between this input and output was controlled by a secondary input VC. Right? Here, you are not giving any voltage input other than the control voltage VC. Okay? Is that
The
fine?
VC itself sets the frequency of the
VC determines the oscillation frequency of the VCO. Right? So the output will have some oscillation frequency omega out. This will be a function of the VC. Okay. All right. So we were looking at a VCO with input connected to a particular VC voltage, and this was equal to, do you remember the voltage we gave? Vm into cos of omega m t.
We discussed in the last 10 minutes of the lecture.
Yeah. Okay, and then we saw how to write an expression for V out of t. What is V out of t? This is some A cos of the total phase, where the total phase is omega naught t plus integral of kVCO into Vc of t dt, right? And this came out to be kVCO Vm by omega m into sine of omega mt. Okay, so I had left with a question on whether you can plot the frequency spectrum for V out of t. Did you plot it? Can you give it a try now? You can assume the narrowband approximation, wherein this factor is much smaller than 1 radians. Right. So before I plot the frequency spectrum for this, if there was no VC applied, then the signal would be simply A into cos of omega naught t. Right? How would the signals, if I were to plot it versus frequency, how would it look like? Yeah. At f naught and at minus f naught, you would have the impulses A by 2 and A by 2. So I am plotting only the magnitude. Correct? So now your the cosine waveform, it's going to vary by a small amount, right? All these edges are going to shift around its ideal position. Then what do you expect to see?
the Fourier transform should also shift.
What shifting do you expect to see here?
A small spread across.
So that is a question. Do you expect to see a spread or something else?
If you delay in time, then exponential terms comes in transform.
But it is not a constant delay. The whole signal has not been delayed, right? So if I plot a cosine waveform like this, what happens at this edge? The ideal cosine waveform is, let's say, the white waveform. Now I want to know how the V out of t looks like.
Okay, at that time that will have some small value. So
Is it, just tell me if it's going to advance or delay.
phase will be more.
So this is going to advance. Okay, let's say this is advancing by some delta t. What happens here?
It has to go in front of a delta.
This has to go. Will this advance or delay?
Delay.
This is going to delay by the same delta t, right?
Yeah.
So now every edge is going to follow a similar pattern, right? So there is some jitter, but the jitter is very deterministic.
What do you exactly mean by deterministic?
It can be completely predicted. You can determine the value before the jitter even happens. I can determine what is going to happen at t equal to 10 nanosecond, even at t equal to 0
Because
nanosecond.
we know what delta t is, so like at the next instant.
We know the full expression for it. There is nothing random about this behavior, right? So there is some jitter, but that jitter is very deterministic and that jitter is very periodic. Is that okay? Because the jitter is being contributed by this factor, which means when I look at the spectrum, there is something periodic happening in time domain. So I should see impulses corresponding to those frequencies, right? Now it's only a matter of where I will see the impulses, right? Do you get that intuition? It will be at f0 plus fm.
How do you know if the edge delays, advances in that set will definitely delay on the other side?
So if this is some time, right, I would put the time value here and see if this value is positive or negative.
Okay, it's always deterministic. You don't know if it's without details, you won't know whether it's delayed.
Once I put in a time value, then I know whether it is advanced or delayed.
Yeah, I meant without details about omega naught and omega n exactly.
That we cannot know. Yeah. You need to know the full details. Right. Okay, so now let us, yeah.
When you were saying it's the delayed, so the time will be negative.
It's not that the time is negative, sine of omega mt has to be negative.
Give this question in one of the practices. Additional questions.
This question was given. I don't remember.
How the adjacent shifts when it's a into a of sine.
Yes, it was given as a. But in that, the idea was to recognize that if you are not sampling with high enough frequency, even a higher frequency jitter will look like DC.
But in that
Something similar was there. Yeah. So now I can expand the cosine term. I am going to call this term as some alpha. So this gives you a cos of omega naught t into cos of alpha sine omega mt minus a sine of omega naught t into sine of alpha sine omega mt. Then you apply the narrowband FM approximation. This term becomes 1 and this term becomes simply alpha into sine omega mt. So you have a cos of omega naught t minus a sine of omega naught t into alpha into sine of omega mt. And then you expand this and what do you get? Alpha a by 2 into cos of omega naught minus omega m into t minus cos of omega naught plus omega m into t. Right? Now I can plot with respect to f. I'll plot V out of j omega. So at f0 and minus f0, you will see a by 2. That is coming from this expression, right? Now at omega naught minus omega m, that is f0 minus fm on either sides, what do you have? Alpha a by 4. And corresponding to f0 plus fm, you will again have alpha a by 4. So now if you wanted to look at the PST, you simply have to square all these magnitude terms. Now, did anyone write omega on the x-axis and still used a by 2, alpha a by 4, etc.? That is incorrect, right? Once you draw it, sketch it with respect to omega, the magnitudes have to be pi by 2, etc. Pi a, the area under the impulse has to remain the same. So the peak value you write with respect to f and with respect to omega are different. Yeah.
Here we got 3 impulses because of narrowband approximation.
Correct.
Otherwise, we would get a spread.
Otherwise, would it be a spread?
There will be multiple smalls for this. It won't be continuous games.
I am not sure if it would be a spread because there is still periodicity in the output. So I would still expect to see strong tones instead of a spread.
We can expand those cosine and sine terms like the Taylor expansion or something and then take the terms so there will be significant discrete parts.
You can try. Yes. Shall I give that as a homework? So what is the statement you've made? We expand this using Taylor series and then?
Not take the approximation and take the Taylor series and then multiply each term and then see.
So why don't you all try this as a homework?
But that will give definitely the tone only, right?
That will also still give tones. Yeah. You will still have expressions of sine and cosines. It will still have strong tones. Right? But
that won't be the approximation.
that is depends on how many higher order terms you are taking, right? You will still end up with an approximation.
But why would if you integrate an impulse, you always get the same area, whatever the variable is there.
That is true.
So why do you
I can want to try.
Why is that so?
If I give
What is the relation between f and omega?
by 2
Yes. So if I take a small band here versus a small band on the omega axis, they will be scaled, right? So the same accordingly
it would get a df and then d omega. Df by omega.
So this happens only when you deal with the impulses. For all the other values, it is fine. Okay, so now could you quickly tell me what is the ratio of sideband magnitude by carrier magnitude? Okay. So this is equal to alpha by 2, which is
VCO Vm by 2 omega.
KVCO Vm by 2 omega m. So let's quickly do a sanity check. Is it dimensionally correct?
Yes.
What should be the dimensions on the LHS? Unitless. What is the dimension on the RHS? Is that clear to everyone? What is the unit of KVCO?
But KVCO into V is also unitless. Is omega radians.
So what is the units of KVCO? Is it radian per volt?
per second?
Radian per second per volt. So omega out is omega naught plus KVCO into VC. Together what is the unit? Which is radians per second. Right? So KVCO should have radians per second per volt. So then you have this as volt, this is radians per second. So it cancels out, it is unitless. Now, does it make sense intuitively? What happens if KVCO goes to 0?
There is no sideband.
There is no sideband, right? Which is what you get from here also. What happens if Vm goes to 0?
That's same thing.
Same thing, right? What happens if omega becomes infinity?
What omega m?
Omega m.
That is.
Omega m is so high that even Lord Jitter is not able to give a sideband.
I think if omega m becomes infinity, our approximation itself might fail. So that was a trick question. Okay, so now we take the same VCO, but instead of connecting a deterministic source at the VC voltage, we'll do something interesting. So I have taken the VCO, instead of connecting a deterministic voltage source, I connect a resistor. What do you expect to see? Just a resistor R.
variable current flowing through the resistor.
Why variable current?
V out will be changing. Okay,
There will be spread around the ideal
You'll expect to see a spread around F naught. Why?
VN, because it is a non-deterministic noise signal that we are using.
So let's see if we can see what he is telling us, right? So because it's a resistor, it will have thermal noise, which I can plot as Vn square, and I put a ideal resistance, right? So now I am interested in calculating what is the voltage domain spectrum here, right? The first step to do that would be to calculate the phase domain spectrum here. Okay, so I know that there is some PSD at the input. I want to calculate the phase domain spectrum here. How should I proceed? Find the relationship, right? So I have to find the transfer function from this input to the output. Okay, or in other words, I have to find out the transfer function from Vn square F, or a small voltage fluctuation at the input of the VC, to the phase at the output.
why not like SVA? Not possible.
So when we calculate the transfer function, we treat everything as deterministic signals and then calculate the transfer function.
Yeah, I'm saying why.
I can write this as SVF. You want this to be written as
No, I'm
SVN
saying,
of F.
why are we going to phase domain right now?
How would you calculate it? The relationship you have for the VCO is between omega out and VC. Right? Yeah.
But if you connect a resistor to ground, I get that the resistor value will change with noise, but how does that
Resistor value does not change with noise.
Then how is there a voltage being applied? If you're just connecting it to ground, how is there a voltage being applied?
So even if I take a resistor which is unbiased in all sense and I look at the voltage drop across it, ideally you would have expected it to be 0. But you will see that there are some small voltage fluctuations. So now the voltage fluctuations are going to be around 0. Is that what is causing the doubt?
Yeah.
So the voltage fluctuations are around 0. If you want, we can add a bias voltage like this. So now this is going to cause voltage fluctuations around some VC0. So we know the relationship between phi out of t and VC. What is the relationship?
Omega naught T plus.
Okay, so omega naught is omega naught t. Omega out is omega naught t plus kVCO into VC. So what is this relationship? Total phase will be integral, which is omega naught t plus kVCO, integral from 0 to t.
Ma'am, again doesn't make sense.
VC.
Omega out should be omega naught plus k, not omega naught t.
This is t is not yet. Yeah, right. Okay. Now this term can be written as some operating point plus the small signal phase. So here this part contributes to the operating point and this part contributes to the small signal phase, which we called as the excess phase in the last class. Okay. So now can you tell me the transfer function between excess phase and VC? So if I take the Laplace transform, this simply becomes kVCO by S into VC of S. So now you know the relationship. So if I give VC of S, I get phi x of S. Once you know this relationship, you can directly tell me what S phi of F is in terms of SV of F. So this into magnitude of the transfer function the whole square, which is kVCO square divided by what is S?
Omega 4 pi square.
So this is, so magnitude of S will become 2 pi F, right? It is j omega, so I take the magnitude. So this gives you 4 pi square into f square. So I'll bring out all the factors that are independent of the frequency. So SV of f divided by f square. What is SV of f? This is a resistor. What is the voltage domain PST for the thermal noise? 4 kTR. So this gives you kVCO square divided by pi square kTR into 1 by f square. So you had a white noise PST at the input and you are getting 1 by f square PST at the output. At the input, the PST was flat, it was white noise. How does S phi of f look now? But around origin, you will have a 1 by f square shape, a scaled 1 by f square shape. So how does SB of f look? It is going to get shifted around f naught, right? Whatever is the operating oscillating frequency of the VCO, the S phi of f is going to get shifted around that.
What is the relation between SVF out of F and SVF?
So we derived this. Why don't you look at your notes? So if you don't have your notes with you, assume that the output V out is some A into cos of omega naught t plus some thermal noise. That is causing a phase noise. Do you remember how the relationship turned out?
Was by 2 pi something by omega naught, there was some scaling.
So we assumed narrow band approximation here, right, and expanded this. And do you remember what you got? So you got A cos omega naught t minus some A into, I think you had some sine of omega naught t into phi n of t.
Yeah.
Right? There might be some factor missing here. Right? So this of course is giving you impulses at f naught.
Yes.
Right? What did this give you? So the PSD of phase noise was translated around f naught.
Yes.
Right? It was translated as well as scaled. So if I look at the, so if I have S phi of f like this, around origin it is some shape. Now my SV of f, so I will plot the one-sided PSD. So around f naught I will have the impulse.
SV out of F, right?
This is SV out of f.
S phi of f contains both excess phase as well as total one.
What is total one?
Here the phi excess of s which we calculated.
So S phi of f refers to the PSD of this quantity.
Which we are denoting by phi x.
S phi of f. So if you are getting confused, I can write it as S phi x. Is that okay? Right? And then you would have the S phi x of f translated around f naught.
Here F is your phase frequency. F is your phase frequency.
F is the frequency content in the phase signal.
That's omega naught by 2, whatever it was without this.
No, f is the, so by f I think he meant this f. So your excess phase is now some waveform with respect to time domain. I am looking at the frequency content in that waveform.
Just of the excess phase.
Just of the excess phase. Because the operating point phase we know is going to increase linearly. Omega naught t.
So,
Right?
like, what would be that S phi total of f? Like, that would be increasing in the if we try to plot S phi total of F.
So that is a ramp signal plus some random signal.
So that would be a ramp plus this.
The total phase is a ramp plus a random signal, right? So because one of the quantity is random, you will still have to look at its PSD. So you'll have to look at the PSD of the ramp, and to that you have to add the PSD of the excess phase.
So in this S V out of F, we are plotting it with respect to the total phase.
S V out of F is the total voltage domain signal. So it's a cosine waveform with a jitter.
Okay. So we are like cosine of the whole of the phase.
Cosine of the whole of the phase. So does this result make sense to you, or is something troubling you? So we have,
The noise goes to infinity.
It is infinite power.
yeah, the noise goes to infinity. What else? This is, so we have derived this result based on the narrowband approximation. What else? Originally we had said that if I take an ideal clock and if that clock had jitter, right? If it was an ideal clock, we would have expected to see an impulse at f0, right? Now if the clock has jitter, the period is changing from one cycle to the next. The period is changing very slowly such that on an average, the period is t0. Right? Then we said that this should intuitively mean that the power is now getting distributed around f0. Right? So this is the result we have based on our intuition. But this is the result that is coming out of the math. Is the confusion clear? This is what we would have expected to see, but this is what we are getting. There is an impulse at f0. We also see infinite power around f0. So what do you think is happening?
Around F0, the approximation is not valid.
Around f0, the approximation is not valid is the exact correct answer. So if we were to do this without making a narrowband FM approximation, right? So you take the cosine waveform with jitter, do autocorrelation, then take its PSD, you'll see that the spectrum comes out to be a Lorentzian spectrum, right? And that Lorentzian spectrum has this shape, right? So it's not that the narrowband FM approximation is completely useless. For delta f's greater than few couple of hundreds of hertz, both these plots are similar. So if I look at some delta f, which is greater than few hundreds of hertz, and I look at the power here, for the same delta f, I look at the power here, the results will match. But as your delta f comes closer to f0, then your results will begin to diverge. But narrowband FM approximation is a very nice tool. It allows you to intuitively, quickly think about how the signals are varying, to quickly plot the phase noise spectrum. So we will still use it, but we will stick to delta f's greater than 1 kilohertz. Right? The moment you come below that, maybe you should consider whether the approximation is still valid. Is that okay? So now we will come back to the CMOS inverter. We are going to assume that the CMOS inverter has some supply sensitivity. So this is our approach. We'll first look at CMOS inverter, see how the supply sensitivity is going to result in a phase noise spectrum. Thermal noise will cause a phase noise spectrum at the output. And finally, flicker noise is going to cause a phase noise spectrum. Cascade enough inverters, you get a delay line. Then we can quickly analyze the same for a delay line. Then we'll make this inverter chain into a ring oscillator and quickly analyze the same factors. Okay, so we start with a CMOS inverter. Let's assume that the supply voltage is not a constant ideal supply voltage, but it has some noise riding on it, which means I can write it as VDD plus some Vn of t. And this Vn of t will have a voltage domain spectrum given by SV of f. Now I am interested in the phase domain spectrum at the output caused due to this voltage noise. How do I proceed?
Make a small simulation and find the relationship.
Correct. So what is the relationship I have to find?
We have T and we out of the
If I am interested in the phase noise spectrum, I should look at Vn of t and the corresponding phase noise at the output. Okay. So now I need a relationship between Vn of t and phi n of t at the output. Any comments on what this relationship is?
should be the integral of that.
Have you seen a relationship like this? Voltage changes, delay changes. Did we call that factor as something? KDL is between VC and delay, right?
This is VCO.
This is VDD.
This is like VCO, right? We are checking VCO and
This is a single inverter. No?
this characteristic looks like a VCO characteristic. So if we are changing VC and we are getting a difference in the phase.
That is partially true. But okay, so you are saying that I changed the VC.
This model looks similar to the VCO.
The reason you are saying that is because I changed VDD. Is the frequency changing? Do you remember the term KVDD?
Frequency will change, right?
I
And
give-
it will change the TP, right?
It changes the delay.
The frequency is function
Only
of-
if I connect this in a feedback. Right? So, do you remember the term KVDD? We had defined a KVDD when we were discussing the supply voltage sensitivity of the DL, right? Especially for the VCDL. So, similarly, we will calculate what is the KVDD, and so what was the expression for KVDD? Change in the output phase when you make a small change in the VDD, right? In other words, dou phi by dou VDD, right? So you can calculate KVDD. It's possible to theoretically calculate it, but this is also a very nonlinear behavior, much like how the TP versus VC behavior is for this is for a VCDL. So what we typically do is you would vary VDD in small steps around VDD and plot the delay versus VDD, right? And then you take the first derivative of that curve and look at the value corresponding to VDD. That is your bias point. So I will change my VDD, right? And I will plot the delay of this inverter. Let's say I got a curve like this, right? Now, if I am operating at, let's say, VDD equal to some VDD naught, right? This is my bias point. This is what I expect this value to be ideally. So I simply find out what is the slope of this curve around this bias point. And that is the KVDD you will use in your calculation. It's a small signal approximation where you linearize the curve around this bias point. Okay, so you find out the value for KVDD. Once you have the KVDD, then I can write my phi n of S as KVDD into the noise in the VDD as a function of S.
Yes.
In other words, my phi n of t was equal to KVDD into Vn of t. So once you have this relationship, you can quickly calculate the S phi of f. Now assume that SV of f was white noise. So this is with respect to frequency. This was some white noise spectrum. Then what is the expression for S phi of f? This is KVDD. KVDD square into SV of f. So if I had a white noise spectrum on the voltage supply, then my phase noise spectrum at the output of the inverter will also be white. It is a scaled value, that's all. Is that okay? So voltage noise spectrum on the VDD is white, then the phase noise spectrum at the output of the inverter is also white. Okay. Now let's look at how thermal noise is going to cause a jitter. Yes.
S5 of F which we have written will constitute of only phi n of t or
this has to constitute only of phi n of t. Why do you have the confusion?
because if you go a little bit more,
Yeah,
because we have a voltage VDD plus Vn of t, right?
correct.
So only we are taking effect of phi n of t only in S5 of
Correct. It cannot be the total phase, right? Because let me consider an ideal inverter. An ideal inverter which is connected to VDD, right? In which case I would expect ideal output. No jitter in the output signal, right? And then its phase signal will simply look like this. For every time period it is accumulating 2 pi. So this is now my bias point. On this bias point, there is some small signal noise riding on the VDD, because of which these edges are going to shift left, right, etc. Right? And that corresponds to having some small signal noise on this. Now I can look at the small signal noise alone. So that will be something like this. So this is my phi n of t. And I am looking at what is the PSD of this phi n of t.
this is overall S5 of F.
This is not the overall S phi of f. This is only the small signal phase. And here that small signal phase is a phase noise. Is that clear? Yeah. Okay, so now if we consider an ideal inverter, if I have an input going from 0 to VDD, then what happens to the output? It goes from VDD to 0. Right? So let's say it goes from VDD to 0 like this. Now, in the presence of thermal noise, what do you think is happening? VDD is a constant. Right now we are assuming thermal noise in the transistor. Current is going to change, right? So, if you are looking at a discharging path, what effectively happens is, so we are discharging the capacitor using an NMOS transistor, right? So, which means I can model it as some current which is getting pulled out of the capacitor, right? But now because the NMOS transistor has thermal noise, you also have some IN square here, right? So IN square, because we are again looking at the PSD. So to understand this, you can simply think of some IN here, right?
But why is current only pulled out?
IN can be positive and negative. Now because of this, let's assume the ideal point where the signal crosses VDD by 2 was some T0. Now in the presence of IN, it's possible that this waveform is going to look like this. It could be below or above. It depends on the value of IN, whether it is positive or negative. So this will result in T1 being the point at which you cross VDD by 2. Or maybe another possible shape could be this. Now this is going to result in the crossing happening at some T2. So because of this, now you have a jitter. Instead of crossing at T0, you are crossing at some instant around T0. Okay. So this is why we have jitter because of thermal noise. Now let's assume I have cascaded enough of these inverters. So let's say one. So, and let's say I gave a very ideal rising edge here. So I expect to see a clock falling edge at O1, another rising edge at O2, falling edge at O3, etc. The first inverter is going to add some noise, some jitter to this edge. Okay, let's say the associated RMS here is some sigma J1. Okay, or in other words, the power in the jitter sequence at the instant O1 is sigma square J1. Can you comment on whether the jitter corresponding to O2 is going to be greater, smaller or equal to sigma J1 square? Why greater?
Because there's already jitter calculated.
Jitter already from the VDD.
There is nothing from VDD. We are assuming ideal VDD.
From the left, there's one jitter, from the right, there's one jitter.
What is right?
Like the left edge of the jitter.
Left edge of the jitter?
There will be a maximum kind of jitter
There
on the
are
left.
Okay.
And there's a big maximum kind of jitter.
One jitter is coming from the input, and one jitter has the own
Uh-huh.
inverter.
So this inverter is already seeing a jittery edge. So it's going to pass on whatever jitter it has seen. On top of it, the inverter is adding its own jitter. Right? Now these two events are uncorrelated, they are independent. Therefore, the jitter here is going to add in power. Right? So it will be twice of sigma j square. Whatever is the sigma j seen here, provided you are operating at the same temperature, right, the thermal noise PST of the transistors are going to remain the same. Therefore, the jitter is going to get added in power as you go through the sequence. So now if you had n inverters in cascade, the total jitter power at the output will be n times sigma j square. In other words, the RMS of the jitter seen at the output will be root n times sigma j square. Okay? Okay, so we can wrap up the class here. Thank you. We'll have a quiz on Monday.
Syllabus after midterm till today.
After midterm till today.